All right, guys. This is where you basically get introduced to the reality of AP Physics. So what we're going to do is we're going to take stuff that we knew from our old physics and we are going to give it a new twist. I'll be honest, the one thing that gives students the hardest time in AP Physics is rotation. All right, because before everything just kind of moved magically, It didn't have size, it didn't rotate. But now we're like, by the way, it has size and it does rotate, and these things matter. So we're going to basically get into the more nitty gritty details. So we're going to talk about rotational dynamics. So all that means is things rotate, move, and change. All right. This is a lot like our old friend kinematics. All right, where we just said, hey, this is how things move, but they didn't rotate. Like balls just kind of slid, or we'd say they'd roll, but we didn't really care that they rolled. We didn't take that into account. And so how do we go from rotational dynamics to kinematics? Now, kinematics is also usually referred to as like linear or translational. All right. So there's a few different things here. So let's talk about how we go from one to the other. And remember how, now I'm going to draw a horrific circle. All right, I know I should use like an auto circle function, but that's not me. So remember how you're like, why do we need to know all this radiance stuff? It's so stupid. Well, now's the time, okay? So if you think of a circle, because that's usually what things rotate on, you've got this angle, and then you've got this value s right here, which is the arc length. That's an arc length, okay? And so if you picture kind of a roll of toilet paper, all right, you've got like this roll of toilet paper, and it starts out, and then as it rolls, it basically goes across, but then it leaves this line behind it, and that line represents the outer shell, aka the circumference of the toilet paper at the time, and that's how it rolls. So what we're doing is we are taking something that was a circle and we are looking at the arc length to figure out, okay, how far would that be in a straight line if it was rolling? And so we have to remember how all this works. So remember that arc length, which is s, is equal to the radius times the angle. Now we need to have a few caveats here so we make sure that we're all on the right page. So let's get some fun colors. All right, so again, this here is the arc length. This is our radius. That's a D, not a US. All right, and then this is our angle in radians. All right, not degrees. All right, so sometimes we're going to use degrees, but a lot of times we're just going to use radians. So just be prepared for that. All right, so that's how we figure out, okay, so how far did it actually go linearly? So s, the arc length, that's kind of like our translational or linear, and we're going to take our angle, which is our rotational component. So let's make some analogies between what we knew and what we now will understand based off of this. Okay, so I'm going to scroll down a little bit. I'm going to erase this line that appeared. Don't know why it appeared. I hate you. All right. So here's what we know from our past. We said, okay, if we are doing with, say, linear versus rotational, in linear, we just said, okay, what's my position or my displacement, right? Position, displacement, blah, blah. Well, now we care about the angle. How far did it rotate? Through how many degrees did it change? Things like that. And the real big one to go from point A to point B is this idea of arc length, because x effectively now equals our arc length, and that is equal to the radius of the circle times the angle. So that's how we get between these two. All right. But we have more than just that. We also have we have things like velocity, right? So velocity tells us how our position is changing over time. Well, we're not going to use the triangles anymore. If you were in my class, then I use the triangles as much as possible. We're going to replace those triangles with some integration, or I should say derivative elements, some calculus. Let's just say we're going to replace some calculus. So I write it a bit weird, I've been told. dx dt. So this is the rate of change in your position relative to the rate of change in your time. Okay? And that is akin, as we have seen from above, x is effectively our arc length, that's our s. So this is really ds dt. And I know I write my stuff a bit weird. Now, if we look on the angle side, all right, then we want to see, well, okay, over on the linear side, we care about how our position is changing. Well, on the rotational side, we care about how our angle is changing. So this is going to be a change in our angle with respect to time. So that's going to be this, okay? And we have a name for that. So linear is velocity. This is a W, but it's not a W. It is actually a lowercase omega for angular velocity. So I'll make a little note of that. But it's basically a W. Just draw yourself a little curly QW and you're good. This is angular velocity. All right. And so if you look at how this works out, the change in your S divided by the change in time, well, the radius of the circle doesn't change unless you're doing the toilet paper, then it technically does change, but let's just pretend it's a ball rolling, okay? So then your radius doesn't change. What really changes is just the angle with respect to time. And this is what we get for our understanding of omega. And so omega is equal to, whoops, says, write that better. That's not what I want to do. My bad. We're starting with velocity, Smansky, do better. So our velocity here, stop erasing, oh my gosh, pen. So our velocity is equal to the radius times this change in angle over change in time. As we said, change in angle over change in time, right here is our angular velocity. So this is basically another equation. And I should go back up here and say this is also one of our core equations. So we're just making analogies between what we know about linear stuff. We're saying, okay, let's put it into the mindset of now a ball rolling or a circle moving, and we're going to put it into rotational stuff. All right, so we've done position, velocity, and there's one last thing that we always have to deal with, and that is acceleration. So let's go and let's talk about acceleration. So angularly, linearly, oh my gosh, it's like my brain's not working right now. Sorry, guys. So acceleration is your change in velocity over your change in time, but we don't use the triangles anymore. We use these guys. So that's dv dt, okay? And then if we look on the rotational side, we use an alpha, little fishy guy. And that is equal to your change in your angular velocity over your change in time. But again, we don't use the triangles, so it's dw dt. All right. And so then if we look at our link between these two, this is change in your velocity. And we already said that this is your velocity right here. Okay. So here's your velocity, dude, right there. So this actually becomes your change in r omega divided by that. And then again, I'm showing you how this kind of breaks down. The radius is constant, so we pull that out. And we replace our triangles with these guys. So d omega dt. And then we can say, hey, look, this is interesting. This guy here is this guy here. So what that really means is that this is equal to the radius times this guy here, and that is our angular acceleration. All right, so then our equation that links linear acceleration to angular acceleration is you just kind of multiply that by r. You get that. So those are the three equations that basically link everything together. And I know the first one kind of disappeared, but it's still right here. All right. So if you want to go from linear to rotational, basically you're just taking the rotational and you're multiplying it by the radius. That's it. All right. It's pretty straightforward. Now, the cool thing is we can then make a whole new series of equations. So I'm just going to scroll down and let's make links between our old friends, the kinematics equations. Yay! I know you guys are like, Mr. Mansky, I really hate you. Kinematics equations. And now we're going to have new rotational. Rotational. All right. Now the kicker is they're the same. All right, so if I just go down the list, here's my kinematics. Your final velocity is equal to your initial velocity plus your acceleration times your change in time. Your final velocity squared is equal to your initial velocity squared plus 2a times your displacement. Then we've got displacement, delta x is equal to 1/2 v plus v sub naught times change in time. Then finally, we've got your final position is equal to, deep breaths, you can do this. My brain's like, I don't remember. Look at the paper. Okay, look at the paper. V sub naught delta t plus 1/2 a delta t squared plus your initial position. This is what happens when you do this in the summer and your brain's like, I should be out jogging or something. No, must do science, must do physics. All right, so here's what we're going to do. We're just going to straight up make replacements. So rotational velocity is omega. So your angular velocity is equal to, your final angular velocity is equal to your initial angular velocity plus your acceleration times your time. Well, your acceleration is now your angular acceleration times your change in time. So we're just doing straight substitutions. All right, your v gets replaced with an omega. Your a gets replaced with a alpha, and your x gets replaced with an angle. Okay, that's all we got to do here. So then we can say, oh, by the way, I can still use this equation. Final angular velocity squared is equal to your initial angular velocity squared plus 2 times alpha times your change in your angle. All right, I mean, that's it. That's all we're doing. We're just doing straight replacement here. So we can then say this one is your change in your angle is equal to 1/2 times your final angular velocity plus your initial angular velocity times time. Time stays the same. Yay, at least one thing stayed the same. And then finally, your final angle is equal to your initial angular velocity times your change in time plus 1/2 your angular velocity times change in time squared plus your initial angle. So everything effectively stays the same. You're just doing a straight substitution for these new equations. And don't freak out, they'll all be on the equation sheet. But I wanted to show you how your kinematics and linear motion can be translated into rotational motion. All right, so hopefully that helped. Them's all the notes, and see you in class.